Good morning, everybody. Thank you for joining us for this seminar. So from Andrei Shvarts, many of you know him or they've seen, and he did his PhD. Okay, I will start earlier. He did his higher studies in Russia, in St. Petersburg Polytechnic University, and next he joined us for a PhD back in 2015, working on computation contact mechanics coupled with fluid flow and contact interfaces. So he defended his PhD in 2019 and got a few awards for his PhD from CSMR and also from French Society for Tribology for the best PhD thesis in tribology. And later he went to this beautiful city of Glasgow for a postdoc in the group of Chris Pierce and Lukasz Kaczmarczyk, who work on MoFEM. MoFEM, it's open source fine common software code existing for 10 years approximately, right? And now Andrei, for a few years, is already a lecturer at Glasgow University, working in advanced finite element simulations and formulations on many topics. So I'm very happy that we can welcome Andrei for this week. He will stay here in Paris, working with Kartik Sharma on this topic of cold rolling and trap lubricant. So yeah, thank you for everybody online for joining us. I hope you can hear us well, and so I'm happy to give you the floor, and thank you for coming. Yeah, please.
Thank you very much, Vlad, for the introduction. Thank you, everyone, for coming, and I'm very thankful for being here. It's a very nice opportunity to come back to the place that I liked so much to be. I'm really enjoying this new space over here. It was one out of many reasons why I wanted to come to see the new lab. But I'm also really happy to spend time with Vlad and his students, and I'm really happy to see all of you coming for my talk and everyone online. I hope I'll make it interesting. Okay, so let's kick off. So I'm a lecturer at University of Glasgow in the James Watt School of Engineering. I'm part of the Glasgow Computational Engineering Centre, and my work is focusing on development of MoFEM. So what I've prepared is just a presentation looking at a little bit of introduction of myself, maybe a bit expanding on what Vlad said and trying to remind you of what I did back here when I was doing my PhD and what I did for my postdoc. But I will mostly focus on MoFEM, trying to share with you some of the ideas and the paradigm behind its development that I hope can be maybe useful in other contexts as well, because I know that there is a lot of effort going on in France in general and in Mien in particular in developing software. So I would be really happy to share my experience that I learned over the years abroad. And then I've chosen two examples maybe to showcase how those concepts are working for some of the interesting problems we've been looking at, like data-driven finite elements, and also a new context-stable formulation. So I chose those two because this is the work of my first two PhD students. One is has completed, and the second one is close to completion. So I wanted to highlight those works as well. Okay. Yeah. Okay. So short introduction about me. My PhD was from 2015 to 2019. It's CDM in Evrim, and it was about coupling mechanical frictional contact with interfacial fluid flow at small and large scales. And so I was supervised by Vlad and by Georges, and also by Julien, who was at that time at Safran Tech. And I did it at Siemens, even though at that time it was called COCAS, I think. Yeah, and so I was quite lucky to get two PhD awards for that work. So the prize from the Association Française de Mécanique and from the CSMA. But surely it reflects not just my work on this, but also all the effort the supervisors has put into this project, and also the environment where I did this. Without all of this, I think it would not be possible. So just, I'm not going to spend too much time on this, but maybe just to give a bit of context what I was working this at the time and what Vlad was pushing for. We're looking into the problem of fluid flow in contact interfaces, and we're not looking into one specific example, a specific application. There was a wide range of cases, but maybe the most obvious is sealing. But also lubrication, and also thinking about biomedical applications where the fluid can be between articular cartilage parts of the joint, tire rod contact, and some geotechnical applications as well, even as exotic as sliding of glaciers. The idea was to implement a framework in that set, which was being actively developed at that time, where we could project roughness on a very refined finite element mesh, and then bring deformable solid with this roughness in contact with a ridge surface, and then study fluid flow in the free interface, free volume between those two, and do this doing very accurate two-way coupling, such that the contact problem defines the gap for the fluid, but the fluid adds additional pressure. And quite a lot of effort was going into developing an algorithm for this, such that at every iteration of Newton-Raphson, we would look into this contact interface, identify contact elements, and then try to look for all the paths the fluid can take from the inlet to outlet. And as you can see, there would be some areas over there which cannot be occupied by fluid because they are closed off. We call them trapped zones. So we had to identify those trapped zones. And finally, we had to put this all into a kind of a monolithic scheme where we have the parts relating to the solid deformation, to the contact, to the flowing fluid, and also to the trapped fluid zones, which were adding additional pressure on the system. And the type of results we could get out of this were looking like this. So we could look into the streamlines of the flow with some intensity, and we could also look into the stress concentrations on the tops of aspirators which are coming in contact. But we could also see how the pressure is increasing inside of the pools of this trapped fluid. And there was numerous pools like this appearing, which were adding to the physics in the interface. Okay, fast forward to me finishing my PhD in 2019, and then I joined postdoc at the University of Glasgow, and we're looking into nuclear problems over there. Actually, I don't know if you know that all the nuclear power plants in UK are owned by EDF, and they produce actually quite a lot of energy, not as much as in France, but still a significant amount of energy in UK comes from nuclear. But a decision was made quite a long time ago in the last century to make those reactors gas-cooled. Means that there is no water inside of the reactor. There is CO2, and CO2 takes the heat from the fuel and then heats the water in a different circuit. And this was found to be more efficient. However, this means that the graphite bricks which are housed in the fuel, they are acting as the neutron moderators, and they take a lot of radiation. And what happens with them is that they crack. And we were looking in one particular way how they can crack, and we're looking into the bricks for a particular station called Torness, which is near Edinburgh. This is my photo. If you go on the train from Edinburgh to Durham or to London, if you go further, you can take a photo like this of this quite beautiful power plant, a nuclear power plant on the sea. It looks quite different from the typical the ones that you will see in France with those huge towers. Yeah, you don't need them because there's no water there to cool down. Everything is happening inside with those gas cooling systems. But the way how this particular bricks crack is happening at the connections between those bricks. And when one of the bricks opens up because of the special stresses arising due to radiation, it can lead to a fracture of this wall over here. And this is dangerous because a chip can appear, can detach, fall inside of the channel, and then later on, if one day they need to stop the station quickly, they would need to put in the control rods, and they might not be able to because of all those chips stacking up inside of the of the channels. So we were looking into the simulation of this kind of scenarios, trying to predict how the cracks start, how they propagate, and how the contact contributes to the driving the crack propagation. And what we were quite happy to observe is that we could replicate the shapes of the chips similar to the experiments. Obviously, this was not on irradiated graphite. You can never look into the irradiated graphite like this. This was in an experimental setup, but we could replicate the shapes carefully. Okay, so that's all I wanted to present about my introduction over here. I want to switch now, talking a bit about MoFEM. So all this work that I talked just before about fracture was done in MoFEM, and MoFEM stands for Mesh-Oriented Finite Element Method. I hope in a few minutes it will become clear why we are mesh-oriented. But right now I want to just introduce you to the people behind it. So we have a group of scientific management, the permanent staff at University of Glasgow, where we supervise the students and postdocs. So we have a group of core developers, mostly myself and Lukas and the postdocs, and then the user modules contributors are our PhD students. So there's also 15 past contributors, so I would say around 30 people have been developing MoFEM over the last decade. We have quite a lot of industry support for this, coming from EDF, that what I was talking about. This project continues, but then also Rolls-Royce, and recently we started working with German companies, Freudenberg and Siemens, and we have our own spin-out called Mesh-Oriented Solutions that we are starting to develop as well. I'll talk about that in a second if I have time. Okay, just to introduce a little bit the paradigm of what we are doing and where we kind of find ourselves different from other codes. So one of the things is that we really want to create the codes ready for industry, and that highlights the industrial support that I have shown in the previous slide. But from the point of development, obviously we want to create a community of people developing it. We don't, as you can see, we are celebrating the code birthday. So in 2023, it was 10 years. And this photo over here is from our headquarters at Pierce Lodge, University of Glasgow, the oldest building there. You can see how the group has grown in 2 years, and we keep growing. But on a more technical side, the idea is that we are trying to implement advanced finite element techniques, and that includes hierarchical approximations. I will talk more about this. Maybe I can show right now an example over here. So if you look into the standard Lagrange chain functions that you find in all the commercial codes, you can construct higher order approximations, but you need to add additional nodes. Yeah, when you go from the first order to the second order, you need to drop those linear shape functions. You need to add an additional node. You need to construct your polynomial functions on these 3 nodes. And if you want to go higher orders, you need to add more nodes. You need to change the mesh. You need to change the connectivity of the mesh. What we are doing with hierarchy shape functions, it means that we can create the hierarchy of high order shape functions based on the same element without additional nodes. So we start with those linear ones, they're the same, but then if you want to go for the second order, we add on top of those linear shape functions a parabola without any additional nodes on the same mesh, without remeshing. And then for the high orders, we'll just keep continuing, keep bringing those high order harmonics, a little bit like Fourier, the composition of a function in infinite number of harmonics. Well, here it's obviously finite, but each one adds to the accuracy. But then we are looking into things like error indicators and adaptive refinement. For example, for problems like this, the microfluidics, where we want to track the boundary between liquid and gas, and we want to refine the mesh there. And in this particular case, it's done using hanging nodes, so we can quickly refine on the fly. We're also doing adaptive order refinement, peer refinement, but what's most important is that we're looking to the mixed and hybrid methods, and this is what I will try to focus on in my examples to show you the benefits of the mixed finite element methods. And these mixed methods are tightly related to the functional space that we're using. Some people call it the RAM diagram, like the full RAM diagram, that we can approximate not only the standard continuous H1 functions, but also the ones which have less regularity and all, for example, only preserve the normal fluxes or the tangential components, or completely discontinuous spaces like L2. And why we are doing this, the whole goal is that by accurate choice of spaces for approximation, you can restructure your algebraic system such that it becomes much more favorable for high-performance computing. I will talk more about this, but the whole idea is to have as many as possible block diagonal matrices where each element is represented by one disconnected blocks, because this is the best thing for parallelization. You can quickly spread it on many CPUs or ideally GPUs. Okay, we don't try to reinvent the wheel. We're making our code compatible with many pre and post processors and solvers, material libraries, and so on. And we try to have some elements of professional software development. I would say probably this is the one of the biggest efforts that they're putting our energy into, because this is required for sustainability of our development, that we have not just the version control, which is a standard thing now, but that we have a proper packet management, we have automatic testing, and we have the continuous integration, continuous development, continuous testing pipelines on Bitbucket, so that every change doesn't break the code. And we have very strict policies on pull requests, that any change coming into the code has to be reviewed by several people, especially nowadays when AI is used. We do put effort into making sure that we understand what the code is doing. Okay, I'm going to very quickly go through the members of the team and the project I'm working on, just to show you the breadth and depth, but I will not spend too much time on those applications. If you're interested in any of them, I'm really happy to have a chat afterwards. So two postdocs, Callum and Ananya, are funded by EDF Energy, and they are continue to look into the fracture, but now they use mixed finite element formulation for fracture. And the idea is that you do not need to do anything with the mesh. You don't need to cut it. You don't need to remesh. The specific choice of approximation spaces lets us propagate the crack using the discontinuity of the displacement field itself. And the whole goal is robustness, accuracy, and efficiency. And I will reiterate on this many times, and I will show examples of how this is used. Ross is another postdoc. He is working with Rolls-Royce, and he is looking into plasticity, and specifically he's looking at the problem of linear friction welding. It's a very violent problem where you see where certain material comes out of the interface. So he's working on developing that. So it has to look to elastoplasticity and large deformations, but also thermal softening, thermal effects. And now he is extending this to look into contact of those pieces coming out of the interface. Leo is one of my PhD students. It's my collaboration with Deep Nano group of Professor Viktor Georgiev, and we are extending MoFEM capabilities to semiconductor simulations, trying to look into different devices, different scales, and Leo in particular looking into deep diffusion and deep density. So density gradient quantum corrections, but also I'm helping him with what I learned during my PhD into adding roughness into the interfaces between different parts. Like here is roughness between an oxide and silicon. He's looking into effects of this roughness on the performance of the device. Another PhD student coming from the group of Vihar is Sifang, and he is looking into simulating more or less the same devices, but from a purely quantum mechanics perspective with the Schrödinger equation. But since our code is quite universal and is not specifically tied to mechanics problems, but can solve any PDE, it's not a problem for us, with obviously with the help of PhD students like Sifang, to extend this to Schrödinger equation or non-equilibrium Green's function. But this is just the start of this work. So two PhD students have joined us last year, funded by Freudenberg. Mohammed is first of them, and he is looking into optimizing tubular structures for braiding for catheters, for medical applications. And he's using a joint method for this. That's the plan of the work, to use the joint optimization to make sure that those tubes work good both in tension, torsion, and can sustain certain kinks happening in those applications and so on. Second Freudenberg PhD student is Clayson, and he's looking at an interesting problem of mechanical seals. So those are the devices where you have to introduce some sealing between rotating parts, but you cannot put any material there because it's just going to be destroyed by friction. So the idea is to keep the interface sealed by the buildup of the pressure in a tiny gap. So that's what he's working on for the moment on the Reynolds equation. But the idea is to couple 3D solids with 2D Reynolds equation, also using the mixed methods. We have a dedicated student Bogdan, funded by Siemens, specifically focusing on porting our code to GPUs. And this is so the other students responsible for creating those matrix structures which are efficient for GPU parallelization, and Bogdan is working on the side of actually coding the stuff happening on the GPU side. And right now he has chosen a library called Cocos for this after several different tries of other available tools. So Kai is another PhD student that I supervise. He is not developing MoFEM directly. He is actually working in the School of Cancer Studies, and he is looking into changes, mechanical changes in flies when they are infected. But he models the infection using some kind of bacteria. The idea for him is to see how the body of a fly restructures and reacts to the infection, and use this as a model of the response to cancer. And a very standard method in this kind of domain is to use atomic force microscopes to do the probes of stiffness of tissues. And what I'm helping him with is to do accurate identification of material properties using finite element simulations. Lily is another student that we have who is looking into problems of pore elasticity together with colleagues at University Pompeu Fabra in Barcelona. And she's developing a mixed pore elastic solver, which can be applicable both for biomedical but also geophysics applications. Malcolm, I don't directly supervise him, but he's working in our group, and he is looking into magma simulations, also using MoFEM. And finally, I think in this deck of slides over here, I wanted to mention our spin-out, initially created by Carol, and myself, Lucas, and Chris have joined him. It's called Measure Solutions, and our first project has been, and still is, in a collaboration with a hospital in Glasgow. I think it's the biggest hospital in Europe, which is doing also research. And the idea is to use VR to help surgeons who plan a surgery on a patient with broken bones, where they can maybe try to assemble those bones together in VR before doing the actual operation. Okay, now I want to switch to the two actual more research problems where I could showcase how the ideas that I discussed before can be applied in practice, just to make it a bit more tangible. So the first one is about the data-driven finite element framework. And this was the work of my first PhD student, Adriana, who has finished very successfully last year. And now the second one working on this is Harry. They're both funded by EDF Energy. So, okay, I already introduced the problems of the graphite, but now I just want to look into this a different perspective. So this is how the maps of the irradiation of graphite bricks look like. And if you look into, for example, the plot of the conductivity versus the dose of irradiation, you can see it's a mess. Okay, there's not enough data, and this data is scattered. And then if you try to fit it, it's not likely that you're going to have very accurate results over there. So our idea was to try to create a method which would use material data instead of material models, but would avoid a black box approach that maybe some of the modern machine learning neural networks approaches do. And we want to try to be able to minimize the errors, but also quantify the uncertainty of the results. Okay, maybe what I want to ask is how many of you are familiar with the data-driven finite element approach of Michael Ortiz? Okay, good. So I will do a very quick introduction of that, but hopefully it will make sense for you. So the idea is that, okay, we were looking into the thermal flow problems. So if you look just in the conservation laws for the thermal problem, that's something you know that should be satisfied exactly. Yeah, this is the law of nature. And the boundary conditions is also you want something that you want to observe exactly. So we're looking into the temperature gradients, and fluxes. Well, obviously cannot solve this problem. Yeah, something is missing. The constitutive law is missing. But constitutive behavior is something that we want to avoid because it's something which is always approximated. And when you start to look into the complex materials like irradiated graphite, yeah, those material models can be a little bit unreliable. But the whole idea over here is that let's say that you have those a huge set of data points, dependence of the heat flux on the temperature gradient. Okay, maybe it would be more accurate if we said that this was one of the components of the heat flux versus one of the components of the temperature gradient. Okay, let's say that you have this kind of data. One could say that probably it's a noise. There is lots of noise. Let's fit this to Fourier's law. Let's find this coefficient k, and that's it. And let's use that, and let's forget the data. Okay, we want to avoid that. We want to do something opposite. We want to throw away this fitting, and we want to use all of this data. Yeah, no material model, no fitting, no black box approach. This is the original idea of Michael Ortiz. And the idea is that maybe we would be able to realize that the spread of the data wasn't actually the noise. It was dependence on some other parameter that we didn't realize before, like temperature. Okay? And that maybe we could have a material law, or not a material law, we could have a model-free framework which would take into account relation, not just between the flux and the gradient, but between flux, gradient, and temperature. Okay, so we sometimes say that finite element method is an art of controlling errors. So this is what we wanted to bring to this data-driven world, if you want, and that we can use the finite element formulations, weaker mixed formulations, for example, to control the errors, to refine only where we need to refine, and so on. And that would allow us to remove the finite element approximation errors from the uncertainty associated with the material behavior, with the data. And then once we have done that, we can properly quantify the uncertainty of the data. And this is where the data-driven approach shines the most. Okay, so in a nutshell, what is the data-driven approach? Is that you think about two domains. The spatial domain, where you have your finite elements, you have integration points, and in those integration points, you have the fields like temperature, flux, and so on. And then you have a material data set. Those are those blue points over here. And the idea is that for every field that you have at the data at the Gauss point in the domain, yeah, you can map it over here in this phase space. And then you can find the closest point from the data set. We use R3 search for that, and we minimize the distance, which looks like that. Okay, and then, but this point from over here might not be satisfying our conservation laws. So what we will do, we will try to map these values from the data set back to our integration point, and we will try to minimize the functional, bringing the values at this integration point as close as possible to this data set values. But at the same time, we will add conservation laws and boundary conditions as constraints, which are to be satisfied exactly, or in the integral sense. So that we will keep satisfying those constraints, and we will try to be as close as possible to the data set. And we will try to do this iteratively, and we will get closer and closer and closer to the data set. And at the end of the day, we're going to have an intersection of a kind of a hyperplane, which satisfies conservation laws and boundary conditions, with the data set. Okay, so this is the original idea of Ortiz. What we added to this is the mixed formulation, or you could say conservative mixed formulation. Okay, I'm not going to go too much into these technical steps. If you're interested, we have published a paper about this. The main idea is that we formulate a Lagrangian, where we bring this distance to the data set as the part that we want to minimize. And then we add a couple of constraints over here. So this constraint over here is to satisfy our conservation laws. And this constraint over here is because we introduce a new variable. So this is where our new formulation comes in. We introduce a new variable, which would represent for us the gradient of temperature. And then we will solve the saddle point problem, and we will treat properly boundary conditions. Okay, I don't want to spend too much time on these technicalities. I want to clarify the final step of this modifications of Lagrangian, where we notice that there is no more any gradient of temperature. Okay, so we have as a term written nullity. Yeah, we have a variable g which stands for the gradient of temperature. We have temperature itself, but there are no more differential operators acting on T. The only differential operator we have is the one acting on Q with divergence, and then another one acting on Lagrange multiplier. It means we can choose finite element spaces differently from the original formulation. Specifically, we can choose discontinuous approximation for temperature, gradient of temperature, and lambda, because they do not have any differential operators acting on them. And this is actually quite favorable for data-driven method, because you can have different material properties chosen at different points, integration points of your elements. So there could be jumps in response even inside of the element, let alone between the elements. So, but then for the flux, we need to choose the space which allows to compute divergence. That's the space called HDIF. And the intrinsic property of the space is that it conserves normal flux across any inner boundaries. So for free, we get a space which is designed to conserve, to satisfy, let us satisfy conservation laws in the strong sense. But what's also more important, this is the bridge towards this efficiency, is that we get a matrix structure which has a lot of those block elements. Okay, we're still working on this. Harry is now picking up the work on modifying this matrix that almost all the matrix looks like that with those element blocks, but this is particularly good. Okay, maybe just to clarify this, I'm going to use one slide created by Lily for the conference we had last week, to try to explain to you the difference in the connectivity of the, let's say, degrees of freedom for different approximations, but also how they result in different block structure. Okay, H1 is, I'm sure everyone is familiar with. This is our standard finite elements. They are based at the nodes, and then if you take one node, it will have somehow interplay with the degrees of freedom from all the nodes of the surrounding elements. Okay, and as you can imagine, when you do meshing, you can have arbitrary number of elements meeting at a node. And since every connection like this, when the 2 degrees of freedom are contributing to a Gauss point together, means that there's going to be a relation, there's going to be an entry in a column and row. It means that the structure of this matrix will be different for different meshes. It cannot be predicted in advance. It means that you cannot know how much memory you need to allocate when you are assembling such a matrix, and so forth. Obviously, you cannot directly port this to GPUs. You can use some smart iterative solvers, but that's not the best thing for scalability. When you go to HD field, your degrees of freedom are now live on the edges to start with. But there are no degrees of freedom at the nodes. That's why there is a property of conservation of normal flux through the edges, because you have degrees of freedom at the edges. So now the coupling happens through the edge, and now you know that every degree of freedom is talking on the degrees of freedom of 2 adjacent elements. And you know that in 2D, you have 2 adjacent elements which share an edge. In 3D, you also have only 2 elements who share a face. And that's why you have a very predictable structure of the matrix. And this is already much better for the memory allocation, but it's not necessarily the best for high scalability, especially GPUs. But when we come to the fields like L2, where element degrees of freedom are living inside of the element, there's nothing on the vertices, nothing on the edges. It means it's completely disconnected from the other elements. This degree of freedom is not talking to those degrees of freedom. They all separate. They all approximate separately. That's why the matrix looks like this. It's just a block corresponding to an element. And this is the ideal, because you can imagine that how many entries are going to be in those blocks? I don't know, 10, 20, 20 by 20, 20 rows, 20 columns. You can invert them exactly on GPUs. GPUs are ideal for the dense operations on the small matrices. And then you can have as many blocks as you need. You can spread them on the many GPUs, invert, put it back. Okay, you cannot have the whole matrix looking like this. You need to have some mustaches coupling them together, but that could be easily dealt with short complement. I will show a small example of that later on. Okay, but this is efficiency is only one of the aspects. A different aspect over here is that we have high accuracy, high convergence. And then if we compare the original stronger formulation with more classic fields, with our formulation, the weaker one, with the fields that I have just discussed, we see a very different story. In the standard formulation, your temperature will be continuous, your flux will be discontinuous. In our formulation, it's the opposite. the temperature is discontinuous, the flux is continuous, or at least the normal component of the flux is continuous. And what this means is that we can look into the a priori error estimates. For example, they're available for our formulation for both temperature and the flux. And then if we look for the error estimates for the standard formulation, we see that the estimate for the temperature field is the same in both of them. But for the flux, we have convergence with the rate p plus 2, while for the original one, for the flux, it's just p. So we have super convergence with our method because of the proper mixed formulation. But also, I think what's very nice to observe over here is that the approximation of flux for the second order is the same over here in the standard one as the approximation of the flux in the 0th order, which means that it can be pretty efficient. Okay, another benefit which comes from mixed formulation is the error indicators. So I talked about a priori estimates. Yeah, you get that from the very beginning. You know what's going to be. It always works if your implementation is correct. But what's sometimes more useful is a posteriori error estimates, which can drive adaptivity. And I'm not going to go into the details too much. I just want to show you like an example of how we do this. So we get this temperature field, and it's discontinuous between elements. But once you have obtained the solution, you can compute gradients numerically on this field at every inside of the every element and compute them at Gauss points and visualize them. But also we have this field G, which stands for the gradient of temperature, which is approximated separately. And they are somehow close, but not exactly. And this is where the error estimator comes in, because any difference between this field and this field is our finite element error. So we can look into the difference between them and highlight the elements where this error is the highest and refine them. And we can think about refining the mesh or increasing approximation order. Okay, there is more accurate error estimators that we have looked at, but I don't want to spend time on this. I want to jump to an example. So we looked into this graphite model, and we were looking into the problem with some high temperature on the inside and lower temperature on the outside. This represents what's happening with those bricks in reality. And well, we didn't have the actual data, so we generated synthetic data ourselves. We looked into the like a standard finite element analysis with some complex nonlinear material model for graphite, relevant for graphite. Generated obtained the solutions and took the Gauss point values from the fields to generate a data set, and this is how it looks like. Okay, and in future, we want to be able to do this, the same kind of things from the thermal camera images. Okay, so this is maybe the way how our indicators work and how the adaptive refinement is happening. So we're looking into temperature, flux, and then maybe the most interesting is the error estimator and approximation order plots. So first of all, if you look into this corner over here, you know what's happening at corners. You get singularities of the flux at corners. So you see the color in this particular enlarged image over here shows the error estimator, and you see how the mesh is refined around the corner and how the error estimator is dropping. That's good. But then what's also happening, if you look into this picture on the right, you see how the approximation order is being increased in the elements inside. Okay, there is not that much point of increasing approximation order at the corner. It's not going to help. We increased our approximation order on the fly in the middle. And this is where our hierarchical approximation comes in very handy. But what was quite interesting over here is that in some regions where we increased the approximation order, the error dropped to very low values. However, in some other elements, even if approximation order was 6th, the error estimate was quite high. So Joanna spent quite a lot of time understanding why, and the answer came from the fact that she looked into the values of the fields in those regions where we have those high errors. She mapped them to our phase space of the material dataset, and she realized that those points are actually quite far from the dataset. So we don't have enough data. We need to do more experiments with this a particular material to be able to map better the values at those elements. But what it also meant for us that those finite element error indicators are not good enough for quantifying the problems with the dataset. So Joanna introduced a so-called data-driven error indicator. And an example over here, we took a data set and we specifically took out a small portion of it. Let's say, I don't know, our equipment was faulty in that region. There was something wrong with our thermal camera, and that's why that place is blank. There's missing data there. So we did a similar kind of analysis with adaptive refinement, but also looked into this error indicator, which is based on the distance to the data set. Yeah? We compute the average distance from the field values at integration points to the data set and standard deviation of that. And what we have observed is that there are regions where we have this higher average distance to the data set and high standard deviation of that. And what's most important over here is that if we map those points, those values back to our data set, they're exactly in that empty window. So we can identify without actually knowing a priori where are the problems in the data set. So we can tell experimental collaborators, let's do more experiments if you want to have reliable results. But missing data is not the only problem. You quite often have the noise. So we wanted to have a tool which would measure the noise. And for this, we proposed kind of a method of uncertainty quantification based on the Markov chain Monte Carlo. And the idea there was to, to test this, we just got this data set and we add some artificial noise. And the idea was to do our refinement. And since we have done the refinement, we are very efficient in getting accurate results. So we can try to perturb the resulting fields and solve again, and then perturb again and solve again. Yeah, this is in a nutshell what a Markov chain Monte Carlo looks like in this particular case. And if we look into the standard deviation of results after those steps of perturbation, we can see some regions on the mesh where there's a lot of deviation. And again, if we map the values from those regions to the data set, it falls exactly where we have added the noise. So again, we have identified now the noise data in the results. Okay, I don't want to spend too much time on this. I wanted to cover the contact as well, so I will skip those slides over here. And if anyone is interested in data-driven and its extensions, I'm happy to talk about this. The last 10 minutes, I will just look into our work in contact. And maybe I will try to explain this, the main kind of beacons of the development for us, which are to ensure robustness, accuracy, and scalability of our tools. And this is not just about the contact. This is for all of the applications we are working on. But I will try to explain an example of contact what those mean. And we will look into many different contact problems. For example, those ones related to graphite bricks, they have contact originating. We have fracture originating from a contact corner. And I think it's like this. Please remember that. We will see this example later on. I will use that. But we have other problems with plasticity as well, used for forming, linear friction welding that we already talked about, and then triple generators, one of the examples that one of my students is working on. I'll show some results at the end. And then also what we've been doing actually from our spin out with Freudenberg, looking into the bushing and sealing applications. Okay, so the contact problem. Okay. How many of you know the contact problems? How many of you know the contact problem formulations? Okay, good. So I'm not going to spend too much time on this, but the idea is that you introduce the gap function, you introduce the KKT conditions, which govern the fact that the gap shouldn't be negative, you shouldn't have penetration, your pressure shouldn't be positive, meaning that, the normal traction shouldn't be positive, meaning that you don't have adhesion. And then when one is 0, another one is not. So usually you solve these problems using Lagrange multipliers. And one of the methods which is very efficient for this is to use the complementarity function. And then when you formulate the weak form, you have the standard, the internal and external terms. Yeah, the internal is coming from the stress inside, external is coming from the tractions outside. And we add the terms for contact. Yeah, so we add an additional term representing virtual traction, virtual work of contact traction, where instead of the value of the traction, we have Lagrange multiplier. And then we have the additional equation, which we use to enforce the KKT condition. This is just our complementarity function weighted by the test function of Lagrange multipliers. And in this setting, it's very clear which space we can use for displacements. Yeah, okay, we can start with the standard H1. But the question is which space we could use for Lagrange multipliers. Maybe to show very quickly, for example, why this is so important, if you start from the simplest problem that I think several of you have been looking at, a wavy surface of a solid body, which is coming in contact with the rigid flat. If you take continuous shape functions for that, for the approximation Lagrange multipliers, you will see something like this. Okay, you will see a result which agrees with analytical one. Almost everywhere, okay, there are some discrepancies here at the center because I used first order approximation. I know that I can bring it closer if I use either finer mesh or higher order approximation. But look into the problems over here. Look into these horrible oscillations. They're not really leading to any catastrophic instabilities, but they are not nice. You don't get the correct approximation at the boundary between contact and non-contact zones. And the reason for this is the variational crime we made by considering continuous functions for Lagrange multipliers, which are not continuous in reality. People have found solution for this, particularly the work of Barbara Wolmuth and her colleagues, to introduce the dual space. So the idea is that to go into a discontinuous space, or dual space for Lagrange multipliers. The idea is that if our approximation of displacement is in H1, on the boundary, it has a trace in space H1/2. It's called fractional Sobolev space. And the dual space to that is called H-1/2. And there are some special dual shape functions which can be constructed, which are from this space. And that works very well. You get the solution which looks the same everywhere, except for this boundary of contact, non-contact, where it doesn't have oscillations. But we wanted to extend this because this base is not hierarchical. It's very hard to construct high orders. And also, it might have some other issues in some specific cases. And remember, I was telling you about the contact in a corner of 90 degrees. So I tried to replicate this problem. Imagine a bimaterial plate where you have a contact on a horizontal interface and on a vertical interface. And we squeeze it from the both axes with some value of pressure vertically and another value of pressure horizontally. And what you expect is that in this particular symmetric case, you have you know what should be the values of the contact pressure on this interface and what should be there. So if you try to approximate this this problem using continuous standard shape functions, we used 4C code for this. You will see oscillation. So in this first part of the interface, I'm showing the horizontal part, yeah, from -2 to 0, and then from 0 to 2, I'm showing the vertical part. So you know what it should be. It should be 0.1 until the coordinate 0, and then it should be 0, 0, 1 later on. But it's not that, because our shape functions can't approximate this discontinuity. And even if we use dual shape functions, we see something which doesn't look too good. There's no oscillations there, but they kind of smooth out this jump. They are based at the nodes, as you can see in this construction over here. Yeah, they are still based at the nodes, so they cannot approximate this jump exactly. So we want to have something more general. I probably don't have too much time to go into details. I'll just try to explain the main idea that we have the Lagrange multipliers, not scalar, not vectorial, but tensorial. Because we can create this space which looks like stress, but not exactly stress. It's not symmetric. We can construct this tensorial space of Lagrange multipliers, which are in HDIF approximation. And if we take their normal trace on the contact boundary, it will be in exactly this H-1/2 space. So it will be very similar to these dual shape functions, but it will be constructed differently. And all what we need is that we need to go into our weak form and substitute this traction over here coming from contact by this normal trace of this tensorial field of Lagrange multipliers. And the trick is to approximate those Lagrange multipliers in the elements adjacent to the contact zone only. So all what we need is to compute this traction through this boundary. So for that, it's sufficient to have degrees of freedom only on the contact edges. And we can still compute the shape functions of those degrees of freedom in those adjacent elements. But the degrees of freedom will live only at the edges, not at the nodes, not at those internal edges, only on the edges exposed to contact. And by using this formulation, okay, we can formulate still our terms for contact, for virtual work of contact. They look a little bit longer, but they have exactly the same meaning. So and we still have this weighted complementarity function. So in many ways, it's similar. It's just a different approximation of Lagrange multipliers. Okay, I just want to very quickly show how they look like. Yeah, so we have, if we consider one element with the contact boundary and adjacent domain, we can see the vectorial base function for this HDF space. For order 1, it's just the, well, it's vectorial, so it shows, it can be shown with arrows. This is the only base function which has flux or traction through the stop boundary, and it's normal, has normal trace on the boundary. But we can go higher orders where they start to have the shapes like this, and it gives us the linear trace on the boundary, and we can go to higher orders, order 3, it becomes parabolic on the boundary, and so forth. Okay, I don't want to spend too much time on the numerical implementation just now, so I will skip that. I just want to show you the results, which are looking very nice, where since we don't have those Lagrange multipliers at the nodes, we have them only at the edges. It means that we can represent the jump of our contact traction between this part of the interface, where it should have this value, and this part of the interface, where it should have 10 times smaller value. We can represent this with our formulation exactly. That was robustness. Now for accuracy, it's about convergence. So we could look into some classic problems where we have an analytical solution for the contact pressure. We can look to the a priori estimates for the error of expected error of the normal traction, and using our hierarchical approximation, we could test the convergence by when we are decreasing the element size for different orders, and we recover the expected estimate for the first order, but then we increase approximation order, and we have a higher and higher slope, which is consistently increasing by 1. This was for the case for the full contact. It's quite more complex for the case of partial contact. There are different estimates for this case as well, and we could recover them and keep improving if we increase approximation order. Yeah, so we are sure that we have accuracy of this formulation. And final part is the scalability or efficiency. And this comes from the fact that we could construct a very efficient solver. You know that when you have a saddle point problem like this, you cannot apply iterative solvers. Okay, you cannot apply direct solver for this if the problem is too big. Okay, you can use MUMs for the problem with tens of millions of degrees of freedom. The memory required would just go through the roof. You cannot apply iterative solver to this matrix because it's not positive definite. It's not going to work very well. You need to do something. And what we do is we use the Schur complement. And what helps us is that those degrees of freedom, like I said many times already, they live on the edges. And the property is that they don't talk, those elements don't talk to each other. There is no continuity of destruction between the two elements. So that means that when we take the degrees of freedom from Lagrange multipliers, they form this beautiful block diagonal part of the matrix at this lambda block. And that's why we can assemble the Schur complement, which is by itself a very useful technique. But what we can do is that we could very efficiently assemble Schur complement using inversion of this matrix D element by element. Yeah, because those blocks are disconnected, you can invert each one of them separately and then construct the Schur complement element by element, which is much more efficient way of doing so when you have a highly parallelized system. Okay, then we do the usual steps from the Schur complement, and at the end of the day, only things which are being inverted to obtain the solution for displacement Lagrange multipliers is this matrix D, which is inverted exactly, and then the Schur complement itself has a nice structure. Now we have the nice structure for iterative solver, and we can use the best ones available, like algebraic multigrids. And this is where this is applied to the problems of tanks, work of my student Tanzib. If you're interested in this application, we have an archive preprint, which is hopefully soon will be published. But the idea is that we need to look into very accurate roughness. Yeah, those are devices which produce electricity from the charges appearing in the contact spots between the two layers. And the goal is to look very accurately into this representation of roughness to get very accurate maps of the contact area and their evolution. And this needs highly parallelized methods of solving this kind of problems. So this is some scalability study, and I could show how nicely our approach with Schur complement and algebraic multigrid scales, so that we are very close to the ideal scaling, much better than direct solver MUMs. And also the memory required to solve with our method is much lower than MUMs. And I just want to point out over here, if you look at this result over here with 128 cores, we are solving one load step of this problem over here with this representation of roughness with this number of nodes at the contact interface in about 1 minute. So if you want to do 10 load steps for this particular mesh, it will take you just 10 minutes. And in 10 minutes, you will get results like this. Okay, maybe a bit longer here because this mesh was larger, but this could be very efficient in getting the results. But it's not only efficient with everything I said before, it's also robust and accurate. So when we compare our results to experiment, we are getting much closer than any analytical approximations with which we still agree in their asymptotic limits. Okay, I think I want to finish with this, and I hope I was able to convey with this example of how we try to tackle with our formulations and our implementations robustness, so that no pre-processing is required for the meshes and for any particular contact regions and so forth. Accuracy, that we can have our higher order approximations, which could be adaptive, could be refined on the fly. And finally, scalability, that we choose the spaces and we choose the structure of our matrix in a way that is most efficient for the modern HPC architectures, specifically GPUs, which are not about solving large complex problems, which are about solving small dense problems. So we can manage better how we distribute our problem between many small cores with little memory. Okay, I think that's all. Thank you very much. Sorry. Go ahead.
Thank you for the presentation. I have a doubt about when you feel the data, like one, I don't remember. And you show that you have a lot of data, and you say you can feel the data. First thing, I was wondering how the data is filled and the accuracy of these data. I was wondering also if it's very important. Yeah, there. It's missing that. I was wondering if, for example, it was possible to say artificially, I would say that I have some missing data here that in fact you already know. You try to retrieve this new data and verify if this predicted one corresponds to the original data. That is my question.
Yeah, I think it is. I agree. This is a kind of an artificial experiment. That's why we are going ahead with trying something coming from the real data. But obviously, the results that you're getting in this region are not trustworthy because this is what we identified over here, that there's a lot of variability in the field values in those elements, and they're actually picking up different values from the data set. So I wouldn't be able to trust that. So if I got it right, what you're suggesting is try to say, okay, let's do another synthetic experiment. Let's fill that missing block and see if this disappears. Well, I don't have the results to show of doing that per se, but I think that Joanna did this kind of things, and well, you would have what you expect. You will have the same plots as this ones without that highlighted region. But okay, it's a good example actually. Thank you. Maybe we'll make one more step of showing how this fixes things. But I just want to say that maybe what we're doing over here was the first step. We didn't really work with the data how it would work in reality, because synthetic data is one thing and real data is different. And I didn't have time to talk about this, but there are extensions of this method, which is called data-driven identification, which helps you get the data from, for example, knowing only stress, to get the stress from only knowing strain, from maybe digital image correlation, and knowing the external interactions and the boundaries, you can infer both stress and strain and use that for the data set. And we want to use that to be able to say, can we actually work with the data sets? Can we actually identify the issues? And can we fix them?
The question about this, the same slide, is this temperature?
So here there is no particular material reference frame, right? So we have GX and GY data all along, but probably if the material has its particular anisotropy, how do you deal with this data-driven stuff? Because here you have so long, but you don't have some reference orientation of right the material. Because maybe this irradiation somehow the regional construction of graphite has some intrinsic anisotropy.
Yeah, of course, most likely it does. But actually, what we did over here, we didn't consider the case that it's isotropic. Like we didn't require it to be isotropic.
Yeah.
So it's just that for the lack of space, I showed only that one. I could also show you the view of the GX component versus, as you can see over here, it's G. That's the gradient GY, gradient GX, but I could show you all the other ones. So they are from the way how they were generated, especially when we consider the noise, they wouldn't be the same in all directions. So we didn't assume that we're looking into the homogeneous material and isotropic.
But the symmetry is kind of the hedral symmetry for the high structure. The orientation. For example, if you construct the same map for one zone and another map for like pi plus 6 Amentum, you'll have a different maybe rotated map.
But what stops us from combining those two data sets together?
Yeah, I don't know. Which follows the material orientation, following some symmetries from the problem from the mesh.
I see what you mean. I have to think
I
about
also
that.
have a question on this subject.
Mhm.
So thank you for this fantastic talk. You are doing so many things and many aspects are useful for us. Regarding this data-driven application to thermal conduction, I am a bit puzzled because in reality, the Fourier law is never questioned. In thermal problems, usually you take Fourier, you don't have nonlinear Fourier. It's most of the case problem of measurements, and the real problem comes from the boundary condition, from the exchange coefficient H for the convection. And this is where probably data-driven would be useful because we don't know so well how to model the interaction at the boundary. And here, you did not really discuss that, this boundary condition of convection.
Right, yeah. Thank you, Simon. Right. I didn't discuss that. We didn't look into the convection over here. This can be done. We were thinking about this. I think there may be some works already in that direction. So this could be extension of the data-driven method. Yeah, so any material property like the H in Newton's cooling law, yeah, can be used, can be removed from the problem formulation, and instead we can do this search in the data set instead. So you would couple in that case flux with the temperature difference, yeah, on the boundary between the temperature on the boundary and the ambient one. Yeah, this could be done. But on the first part that you said, I maybe want to expand a little bit. Well, Fourier law by itself maybe is well established and can be used in so many applications. But for the complex materials like irradiated graphite, you see the coefficient of conduction depends on both the temperature and temperature squared, and that gets tricky. And with some of the plots that I have shown before, where also conductivity depends on level of irradiation, it gets even more complicated. So with data-driven framework, it's very easy to add an additional dimension to the data set, for example, neutron dosage. And then that's something that Fourier's law cannot include.
Okay, thank you.
Thank you. Yeah, thank you again, Vlad, for the question about the anisotropy. I have to think about that a bit. I think this could be done. We didn't require isotropy over here. I have to think about what happens when we have different responses in different parts of the body because of that. But like from a gut feeling, it's not necessarily something that would be a problem. Yeah, because if you do measurements, if the material is isotropic, no, so it's homogeneous, but anisotropic, there shouldn't be a problem. The problem starts when it is anisotropic. Sorry, non-homogeneous. When it's non-homogeneous, where different parts of the materials behave differently, then you don't know what to do, which data set to use. That's the problem. Then I think this is I would say, the only limitation of data-driven method, that you need to map a data set for a portion of material which is homogeneous. So I would say anisotropy is not the problem. We didn't assume isotropy over here. It's the homogeneity which is difficult. Like inhomogeneity, which is difficult. If that makes sense. I see what you mean. Yeah, it's a very good question. You're saying like how it's called, Gibbs effect, I think, when you try to approximate a delta function, or even just a jump with many harmonics. No, this doesn't happen. This is a slightly different story over here. Okay, maybe you can think about very special cases where higher orders would lead to oscillations. This happens sometimes, but not in elliptic problems. To a large extent is just a more accurate representation of the field that you want to look at. Yeah, I want to be clear. When we're going for these higher orders, we are not requiring higher continuity between the elements. Yeah, it's like with the standard finite elements. You can have second or third order polynomial, but the continuity is only for the first derivative between the two elements. Same for us. We have this higher order polynomials added. There is no continuity between the elements. Yeah, so we are not going into the direction of NURBS. We're actually going into the opposite direction. We want to have less continuity, as I have showed before. But at least for parabolic and elliptic problems that I've been working on, you are adding those higher orders, and you're just getting more accurate representation. With the crack in particular, with this example that I was showing before, when I was showing this animation over here, we did adaptive peer refinement, that there were several layers of elements around the crack where we had high orders. And let's say everywhere we had second order, and then there was a layer around the crack with third order, and then another layer close to the crack with the fourth order. And this was just only improving the stresses around the crack tip. But actually, it wasn't improving them enough. And when we wanted to replicate analytical solutions for a cracked specimen starting at the notch, we had to use quarter point elements. This our adaptivity, when you move the nodes closer to the singularity, then we can reproduce analytical approximations. But for many engineering problems, you don't need that. But I think you can find problems where adding high orders could lead to instabilities. I would say probably in some cases of hyperbolic problems that could actually be difficult. So then you just limit yourself to lower orders. But there are lots of problems when you strongly benefit from this. And crack is not the one where you get the problems. Unless you start to look into acoustics around the crack or something like this, then maybe you would have something more difficult. Well, the elephant in the room is that you have more degrees of freedom that you have to deal with. But what I was talking about, this different structure of the matrix helps you deal with them much quicker. And like the example that I was showing with this contact at the end, when we could solve this huge problem with 5 million degrees of freedom in 1 minute for one load step, was with a second order of approximation of contact on the top of the mesh, and first order for Lagrange multipliers. And of course, we have more degrees of freedom because of that, but you can solve it more efficiently. So yeah, okay, if you don't employ those advanced solvers like algebraic multigrid, the curse of dimensionality coupled with this larger number of degrees of freedom will make things more difficult for you. But when you combine those two things together, then it works. But in general, p-adaptivity is more efficient than h-adaptivity. You converge faster if you increase the approximation order than when you refine the mesh. But it doesn't help you at the singularities. You need to do h-adaptivity at the corners where you have the singularities, and you need to do p-adaptivity where your function is more regular, but you can benefit from the approximation. It does. It does require some thinking ahead. Maybe I will try to open the slide where I'm talking about the libraries that we're using. It was this one. Right. So we are using tools from Sigma. It's a lab in Argonne, I think, at one of the national labs in US. So it's not Chicago, if I'm not mistaken. So they have a library called MoFEM. It's called Mesh-Oriented Database, and they have a very efficient handling of mesh manipulations and handling the access to different geometric entities. To the element, you can quickly get its adjacent edges, you can get adjacent vertices, you can find the bridges to other elements, you can do this in parallel, so you can ask for the adjacencies from another processor and so forth. So we have very quick access to this, and this is integrated into the MoFEM databases, so we map degrees of freedom on those entities. And once we do that, it gets pretty straightforward how you implement those higher order shape functions based on the degrees of freedom which live on the edge itself. Yeah. So the idea of those hierarchical shape functions is that they the value of the degree of freedom of that shape function does not have the physical meaning of the value of the field at the center. Yeah. If you go for the standard shape functions, yeah, the degree of freedom of this N1 is the value of the field at that node 1. For the hierarchical, it is not. It's like an additional correction, like you would do when you add additional harmonics to the Fourier representation. But since we have quick access to different entities in the mesh, and we map those entities to the degrees of freedom, we can get the degree of freedom from this particular entity. We can get the shape function of that, and we can evaluate the Gauss point value of the shape function. In terms of implementation, we don't have to invent them. There are several papers written about that. There are several groups which worked on this. The one prominent one is Dimkovich, Leszek Dimkovich's group in Texas, University of Texas, Austin, if I'm not mistaken. They have a paper 100 pages long, which explains how to construct all of them. And then there is another group led by Mark Ainsworth, who was initially in Scotland, in University of Strathclyde, and then he moved to Brown, I think. And he has papers of how to do this on tetrahedrons specifically. So there are two different schools for doing this. We implemented both, and there's some benefits in each one of them. So there is some story behind this, obviously, but with the structure that we have, it's worked like a Swiss clock, I would say.
As well as hierarchical functions both on the tetra, hex, and other methods.
Oh yeah. So like those papers that I mentioned, I think Ainsworth are mostly on tetrahedrons and triangles. Dimkovich's paper is for everything. The triangles, quads, tetrahedrons, hexes, pyramids, wedges, everything.
Element of the component, right? When you assign volumetric tensorial Lagrange multipliers, every side has its own degree of freedom and its own volumetric representation of this.
It's not a different representation. It's the same field. Yes. We approximate the field in those elements, in those shaded pink elements over there, and then you can approximate it with the degrees of freedom coming from this edge, and you can also approximate it from the degrees of freedom coming from this edge. So yes, when you evaluate it, the Gauss points in these elements, when I didn't have time to talk about this, but we do this integration by parts, and we turn boundary integrals into the volume integrals. We do evaluation if you have a contact both over here and over here, evaluation of this field lambda at those Gauss points in this element would come from those 2 degrees of freedom. Yeah, it's a field. So this field, if I construct this lambda on the whole mesh, it will have degrees of freedom on the edges, on all of these edges, and then also if I go for higher orders, it's also going to be on the faces. The degrees of freedom start to appear on the faces as well. But we don't care about this. For this example, it's enough to use first order approximation. So it's only on the edges. And then I can choose, with our code, as I said, it's mesh oriented. So I can choose on which mesh entities I will have degrees of freedom and where I will have not. So I do approximate this field lambda in the domain, but I choose it to be approximated only using degrees of freedom on the boundary, because it's on the boundary edges, because it's enough to construct the sufficient approximation of the contact traction. Oh. One. No. Only one which has non-zero normal traction for that boundary. For edges, and then when you go for higher orders, that's more amount. There are lots of works where they combine this methodology with some other methods, clustering and inferring from the data set and accelerating the search. But I think in general, this data-driven method, it's hard to answer a question exactly because it depends on the problem. And maybe there are some problems where this wouldn't be the best choice. I don't know, maybe geotechnics problem, when you don't have that much data, you can only drill in one particular place and get information from there. And then maybe this is not enough for you to know. But I think this method shines the best on the problems when you have a lot of data, and think about thermal camera images or digital image correlation images, when you have the whole fields of the data, and then from that you get a lot of points. I can give you an exact metric of what is enough. Obviously, if you have one data point, you're not going to get much. Like you need somehow enough data points which span the all the possible values that you want to have. But even with some of the examples that I was showing over here, you can easily get into the state where, over here, when you start to get the values which are completely outside of the data set. So, okay, you need to add more data. So that's why we were looking, we were bothering ourselves with the same question. So we wanted to look into some kind of methodology which would give us a metric of how bad we are. But I think this is problem specific and data set specific, and that's what you have to deal with over here. Maybe the last thing I want to say, maybe building up of what Samuel asked about using the data-driven for convection. There's actually very interesting work being done on contact. Maybe for those who work in contact will be interested in this. I think it was done in Gianfranco Savalinaris' group. They were using this data-driven methodology to kind of avoid using friction loss. And they were getting some information about the relation between, I guess, tangential traction, normal load, displacement, and so on. And they were connecting them somehow and using the same methodology to infer that. And quite separately from that, another group from Laurent Steiner in Nantes, I think, if I'm not mistaken, is adding contact to the state of what we're showing over here without any data sets. They're just adding contact constraints to these problems. So since I know that many of you, especially working with that interest in contact, there's quite work being done right now on contact modeling for this data-driven.
I think we are done. Thank you very much, Andrei.
Thank you.